Welcome back. In this video, we'll see one simple type of centrifugal governor that is called as watt governor. It is also a pendulum type of governor. So this is the basic structure. So it will obviously have, as it is a centrifugal type of governor, it will have two masses and they will be attached to the sleeve. This is the sleeve, horizontal sleeve with respect to the linkages, and it will attach to the spindle axis. Now the connection of this pendular arm to the spindle, there are three possible types of connections. So one is this: the pendular arm are pivoted to spindle axis on the spindle axis itself, whereas this is another combination possible, that there is an extension, that there is a link attached to the spindle and the arms are attached to this. So if you see, the intersection of the arm and spindle axis actually happens above this actual connection. That is called as open arm type watt governor. And the third possible is rods are actually connected by crisscrossing and they connected above the intersection with the spindle axis. So this type is called as crossed arm. Irrespective of the type, the height h of the governor or this masses is always measured from intersection of the pendulum arm with respect to spindle axis, from that point to the center of the mass. Okay, the vertical distance, this vertical distance will always be called as h, whereas the angle theta, inclination of the pendulum arm, will always be the angle between the spindle axis and the pendulum arm. So that is a takeaway from this slide. So let's next see the force analysis of watt governor. So it's a pretty simple derivation. So the three forces will act on this mass. First is its weight equal to mg. Second is centrifugal force. If the governor is rotating with the speed omega, the centrifugal force acting will be outwards and it will be mr omega square, and there will be tension in this pendulum arm equal to capital T. So when the governor is rotating at constant speed omega, there will be equilibrium set up between these three forces, and from that equilibrium equation we can directly write that T cos theta, that is T cos theta, vertical component of the tension in the pendulum arm. So it will be in this direction like this. So this will be your T cos theta, and that will be equal to mg. And similarly, T sin theta equal to mr omega square. Now here r is the distance between center of the mass and spindle axis. Here this is r, so here this is your r. So it will vary if the speed is varying, but at the constant speed the position of this mass will not vary, so the r will be constant. So next, these two equations, if I divide them, tan theta is equal to mr omega square by g. So it is pretty evident. So it will be mr omega square by mg, and mm cancels out. Okay, so it is r omega square by g. Also, if I focus on this triangle here, so I can write down that tan theta is equal to, opposite side will be r upon h. So tan theta is r by h, and also tan theta is r omega square by g. So equating those two, I will get r by h equals to r omega square divided by g. So from this I can deduce h is equal to g by omega square. I will put the value of g equal to 9.81 meter per second square, and I will convert my omega into rpm, so it will be 2 pi n by 60. So putting both these values, I will get relation between h and the speed in rpm, which will be h is equal to 895 divided by n square in meters, or 895 into 10 raised to power 3 divided by n square in mm. So that is a relation between h and n.